Alright, so in this system we have two masses, which are each of mass m, which are connected by a massless bar, and we're told that each mass is connected to ground by a spring of stiffness k and rests upon a smooth surface. And we're asked to find the equation of motion for this system in terms of the coordinate x, and also to find the natural frequency of this system. So I know when I do equation of motion problems, I'm essentially doing rigid body kinetics associated with Newton's second law. And so in this regard, I want to draw a separate free body diagram for each object in my system. So I can draw one for particle A, and I can draw one, let me just note up here that this is A. Maybe that's a little close to the edge of my recording, so let me move it over here a little bit for you. So we have A, we will have particle B, and we will have our massless bar, which I'll just simply call bar. Okay, so now what forces are acting on A? Well, if A deflects to the right with a displacement x, I know I'm going to have a spring force pushing back of magnitude kx. I'll have a normal force that I'll call NA between A and the bottom surface, and as well as I'll have the weight, which is simply mg. And I know I'm going to have some force, which I'll simply call T sub A, which will act from this lever arm, or this bar that exists. And I know that in terms of kinematics, this thing can only translate, so I'll have some mx double dot I'll draw to the right as so. Now at the same time, I think it makes sense to us intuitively, and we'll prove this with kinematics here in a few minutes, that if x moves to the right, then b is going to move to the left, and so I'm going to go ahead and call the displacement of b to be y, and so that'll be positive to the left, and so I'll have my double dot like so. And so if that stretches out like that, then my force pulling back will be k times y. And I'll have some tension force here, which I'll choose to draw like so. That will be TB. And then I also here will have a normal force between the block and ground, which I can call NB. And I'll have the weight, which of course will simply be mg. And I note, as we'll show in a minute, that x and y will be different because of the two different lengths associated with the little lever arm here. Now if I look at the bar, I know I have to have equal and opposite forces at the end, so I'll have a TA pointing to the left and a TB pointing to the right. And I'll also have pin joints at the center, well not at the center, but at this point O. And I can call that simply OX and OY. And because this is massless, I know that I'm not going to have any terms on the MA side, that is, I can't have any mass or inertia in this system. Now, how do I go about solving this? Well, I go about solving it just like we have a lot of the other problems in this class, and I'll eventually deal with the small angle assumption. So I'm going to start with block A, and I'm going to sum forces in the x direction and set that equal to m times x double dot. This, of course, is a positive to the right summation. And if I do that, I'll have that minus kx plus t sub A is equal to m times x double dot. I can then go to the block B, and I'll sum forces in the y direction and set that equal to m times y double dot. I know this will be a positive to the left summation. And if I do that, I'll have TB minus k times y is equal to m times y double dot. In the case of the bar, what I'm going to do here, because I don't want to deal with the unknown reactions at point O, is I'm going to sum moments about point O. And because the bar is massless, it'll have no inertia, so this is actually a static moment summation. I'm going to choose to do so in a counterclockwise positive fashion. If I do that, what am I going to get? Well, I'm going to get that TA will create a positive moment, and its moment arm will be distance b. And I'll know that TB will also create a positive moment, and its moment arm length will be 2b. And that'll equal 0. The last thing I need here to solve this problem is a kinematic constraint relating x and y. And so in this regard, probably the easiest way to think of this is that initially the bar is straight up, and if it rotates a little bit about this point O, it's now going to take on a dimension something like so. Now why is this important? Well, if x is the amount that we displace here on the top, then y would be the amount we displace this way down at the bottom, where this length here is b and this length here is 2b. Now what does that mean? Well, we can know the interior angle here and here have to be equal. In particular, I can note that if I call this angle phi, this angle here also has to be phi. So remember that the opposite over the hypotenuse is equal to the sine of an angle, so what I'll have here is that the sine of phi is equal to, in this case, opposite over hypotenuse, so x over b, which will also equal, in this case, y over 2b. Now, if these are the same angles, and I'm going to make a small angle approximation here, what we can basically say then is that x is going to equal y divided by 2. If this is the case, then I also know then that x double dot is going to equal y double dot over 2. Now if I take these equations that I call 1, 2, 3, 4, and 5, I can make a single equation of motion for this system and find its natural frequency. How am I going to do that? Well, I can start with equation 1, and if I take equation 1, I'm going to have that TA is equal to m times x double dot plus k times x. I can then take equation 2 and note that that's going to give me that TB is equal to my double dot plus k times y, which by equations 4 and 5 is equal to m times 2x double dot. So I'll write that as 2mx double dot plus 2kx, substituting in, of course, for both y double dot and y. I can take both of those expressions now and plug them into equation 3. And if I do that, what will I have? Well, I'll have that mx double dot times b plus kx times b plus 2mx double dot times 2b plus 2 times k times x times 2b has to equal 0. I'll note that there's a common term here of b, which I can cancel out, so I'll go ahead and cancel out the b's. Begs questions about to be or not to be. Sorry, bad Shakespeare jokes in the middle of the video here. But if I tally this up, what am I going to have? I'm going to have 3mx double dot plus 3 times k times x is equal to 0. And of course the 3 cancels out, so interestingly enough, this just gives me that mx double dot plus kx is equal to 0. This is, for all intents and purposes, simply a very simple spring mass dashpot system. This means if I want to find the natural frequency of this system, it's going to be the effective stiffness divided by the effective mass square rooted, which is simply the square root of k over m. An interesting result from a rather complex system. Best of luck as you work through this and validate this result.